Okay, let's start. So, as it was mentioned that the topic is a comprehensive framework to optimize grid performance of harmonic polluted distribution system. So it's the talk is more on the impact of electric vehicle, how electric vehicle can pollute the grid, and how distributed energy generation DGs can also inject harmonics and all or maybe help the grid like voltage improvement. So before we start talk today, so let me just briefly one slide about my lab. It's a clean and resilient energy system cares.
Yeah.
It's short form is cares, and we started in 2018. We started with the different power system and power electronics and energy system research, but slowly we have moved towards cybersecurity and machine learning and AI side. So we started from power electronics, power system from here, and then we moved to AI, different application of AI, medical system, cybersecurity, machine learning. So right now we have a mix of projects. Some projects are on EV, some projects are on cybersecurity, and then power PLC. So different funnel projects. Uh, So
Can I
yeah,
get you a QR link
EV chargers and grid impact and
for
customized
the
microgrid. So all these things we
link
are
here?
working on. I think there is some
Yeah, sorry for that. Sorry,
no
you
problem.
can go.
This one?
Okay. So today's talk, first we have introduction, and then we will talk about what is difference between charging speed and charging rate. And then we will talk about 33 bus system, which is a case study we are doing. And then in the fourth step, we will talk about benchmarking, voltage profile, and harmonic profile, and then simulation results and conclusion. So let's start with introduction. So as we know that fossil fuel provided benefits such as high power, high energy density, mature technology. So it's been there for so many years. High range and minimal refueling time of electric vehicle. So, but it has some problem. It has all those problem like carbon emissions and pollutions and weather changes and all those things. So to restore the ecological balance, vehicle powered from alternative source are now commercially available. We have different vehicles which are available commercially, Tesla vehicles, which we can purchase, and they are environmental friendly. They're electric vehicle. We do not need to fuel them with traditional fossil fuels. So transportation and energy sectors are the main consumer of fossil fuel based energy. Out of those we have air transportation, ground transportation, and then we have other non-traditional ground transportation like off-road vehicle, tractors, and recently we got drones. So all of these transportation means need power, and to power them we should have electric vehicle which is clean and better. So what are different components of an EV? So we have a motor, we have a reducer part, mechanical part, then we have a battery, then onboard charger to charge the battery, and then we have electrical power control unit to control the power flow. So these are components: motor, which is cycles with the power generated from electricity, simultaneously moving the wheels. So we run it with the help of power coming from battery. Number two is reducer. So this reduce the RPM, controls the RPM. So it's a mechanical part, uh, kind of gear to generate an appropriate level of force. And number three is battery, which stores electrical energy and feed electrical energy to motor to run the vehicle. And then we have onboard charger. This is onboard, I mean, we have the traditional level one, level two charger, which were onboard charger, which converts alt AC to DC to charge the battery. And how about electrical power control unit? So we have low voltage DC-DC converter for bidirectional power flow from battery to and from supply and from AC supply. Then we have vehicle control unit, which controls the vehicle's power control mechanism, and then we have inverter. In converts DC from the battery into AC for uh, to supply it to the motor, and sometimes we also need inverter for bidirectional power flow to grid. And then we have certain issues like in issues range anxiety, inferior acceleration. We cannot accelerate in less time. Affordability, very expensive. Longer charging time. Charging time of EVs is also long. So to make EV performance comparable to that of a conventional fossil fuels, but because that's a catchy thing for people to purchase those EV, unless we can give them the same benefits we have been enjoying with a traditional fossil fuel power vehicles. And to do that, uh, what we have achieved so far. So if we compare, our technology has improved over the period of time. So if we talk about driving range, it has improved from 150 mile to now we have 322 miles of driving range with just one charge. And if we talk about acceleration is how many miles how much speed we can achieve in seconds. So if we can see that Model 3 takes 3.2 seconds to achieve the same speed. So the traditional EVs were taking longer time, but the recent one are much faster. And so miles added in 15 minutes of charging, 15 minutes of charging from DC fast charger, we can achieve 150 miles of mileage. So all these benefits actually make it comparable with the traditional fossil fuel based EV. So that's why we are in a good shape now. Okay, so what is difference between what is comparison between charging speed and charger rating? So as the charger rating increase, charging speed also increase. So this is AC level 1, which were onboard charger. We connect with the AC supply. So they used to take 3 to 5 miles of range per hour. They were very slow. With 1 hour of charging, only 3 to 5 miles of range. And then we have AC level 2 that have with 1 hour of charging have 10 to 20 miles of range only. But recent DC fast charger in 20 to 30 minutes we can have 80% of charge, which is more than 90. This is with less than 90 kilowatt of charging load. So we have achieved a good performance with this DC fast chargers. But then, of course, this DC charger, because they take too much power, so they will come with their impact on the grid. So we will talk about those impact. Okay, so slow charger configuration, which is level 1, which is onboard charger. So these are traditional, onboard chargers, which they're connected through with the grid through electric vehicle supply equipment, Texas Instruments, made by Texas Instruments. So we have inside the vehicle we have battery, and then we have AC to DC converter, which convert AC and charge our battery. So this is within the vehicle. And so how it is made, this is made up of rectifiers. So we use diodes because there is not much control involved. So diode and then buck converter to charge our battery. So onboard charger were designed to provide efficient charging operation with minimum footprint because they are within the vehicle. So our goal was minimum footprint. So we do not add load to the vehicle. So it is designed for small power rating. As the requirement here is to achieve superior performance at a lower footprint. Footprint was important. So we use diodes rectifiers to achieve the results. So compared to PWM rectifier, diode rectifier does not require any gate circuitry. So they are lighter in weight. Generated DC output voltage at the rectifier is then controlled using buck converter. So thermal management and control of charging are the main control objective for this onboard charger so that we do not produce a lot of heat to avoid burning of the vehicle because they are on board. All right, then we talk about off-board EV charger. They're a little bit faster than level 1 charger. So off-board charger are designed to meet the desired charging time constraint, make it faster. High power requirement, high efficiency operations, superior power quality performance, less maintenance are the major constraints. That's why we design level 2 charger, off-board charger. They are off-board, they are not on the vehicle. So they do not add any weight to the vehicle. As charger is located off-board, weight, size are not at top of the chart. That was not a requirement in this case. So even if we have heavier, that's fine. With this specification, mostly diode-based rectifiers are replaced with PWM rectifier, which gives superior performance. So this eliminates any power quality disturbance because we are using PWM rectifiers. And so how they look like, we have off-board charger, and then we have, this is on-board charger. So our vehicle have both capability. They can be charged with on-board charger, or we can bypass them with off-board charger. So we can bypass over here, so to charge our battery. All right, so off-board chargers have different types of, some of them are non-isolated one. We do not have a transformer in DC to DC converter, and some of them are isolated DC to DC converters. So they are single module chargers. They are used for low power charging. If we want high fast power, more power to feed to our battery, then we need multi-model parallel operations. We can have different modules connected in parallel to feed our charge our batteries. So this is for non-isolated one, and this is for isolated topologies. Usually we prefer isolated topologies because transformer is in within that DC to DC converter, which has several benefits. Smaller size, higher efficiency, uh, less weight, thermal management, all those benefits. All right, charging infrastructure. So if we compare electrical EV market is rising. In 2020, we have only 11.3 million EVs. Now, 2025, check the rate. It's 5 times, it will be 5 times more in 2025, and then 3 times more in 2030. So the rate at which EVs are coming into market, so it's also a concern for our electric grid. So development of charging infrastructure is one of the most critical components of ensuring fast EV adoption. Charging infrastructure is one of the most important component. And so adding these EV chargers of different power ratings at different locations to meet different needs to the existing utility grid increases both average power demand and also instantaneous power demand for the system. So on the component level, starting dynamics of DC fast charger, in the start, it takes too much power. So starting dynamics of DC fast charger could also disturb other connected load with the same bus, unless we have starting impact is minimized using storage. If we have storage, in-house storage, or appropriate control so that we can minimize the impact of fast DC charger, starting impact of fast DC charger on other loads connected to the same bus. Therefore, impact of adding EV to utility grids, especially on the distribution side, must be analyzed, as distribution systems are designed with limited overloading capacity. Either we have to add a new transmission line, we have to specifically make a new grid for EV charging. So all these things should be done so that there is less impact. Okay, so let's check the power system profile. So on the left, we have California profile. On the right, we have Qatar. So we are adding Qatar profile because this project was funded by State of Qatar. And so if we see on the California profile, the red one is a maximum demand, and the green one is a minimum demand on any day in a year. So we can see that highest demand is at 6 p.m. And so there is a gap during summer and winter. There is a gap. So that's a problem. So on the Qatar grid, if we see, the difference is even more, because during hot season in Qatar, it's too much load, and during winter we do not have much load. So that's why, although the peak time is also different. Peak time is around 2 p.m. over here in Qatar. So these two geographically different regions have different power demand variations. Ambient temperature is much higher in Qatar, heavily dominates the power demand. So region of Qatar during summer heavily depends on air conditioner to beat summer heat. Because of this, there is a constant power demand post 9 a.m. up to midnight. So there's a constant high power demand from here to here. So high power demand. So California load curve presents a typical mix of commercial, residential, and industrial. So there are three different types of load. That's what we're doing: commercial, industrial, and residential load, with demand surging between 6 p.m. to 7 p.m., unlike Qatar grid. So both have different profiles. And that's the total demand, existing demand, and average demand. So what we did, this is the average demand, 30 gigawatt, and this is the existing demand for California. Similarly, what we did, we thought, okay, let's add EV to this load. And so we want to see the impact of EV charging station on the same existing distribution system. So if we see, this red one is the traditional, the benchmark, old data, existing load demand. And then what we did, if we uniformly distribute EV load 10% uniformly distribute, so check the impact. So this peak will be much higher. So this is 110% uniformly distributed. If we add only 110% on the all timing other than this peak hours 11 to 2 p.m., which is this one, if we avoid adding EVs during that time, we will have less impact on the grid. So that's what we are trying to show, that it has less impact because we are not adding EV during that peak time. So adding EV load to this power demand profile will push existing peak demand further up. This means additional generator will be required. More power should be imported from neighboring grid. So on the other hand, smart distribution of EV, if we distribute it smartly during off-peak time, it will improve the overall profile of the grid. And this results came from this paper. So you can go ahead and read this paper. Okay, so what constitutes a power demand profile? So power demand could come from three different demands. One is, so this is, this is traditional, the original our maximum peak and lower peak for California. And then what we are showing that these total demand is actually comprised of three different sub demands. One is residential range, other one is industrial range, and then third one is commercial range. And the important thing over here is that these three individual load demands are different. They does not look similar to the overall demand profile. So all these three demands have different profiles. So each of these loads have its own variation pattern, different time instants of peak demands, and resulting voltage profile. Even voltage profile is different too. So analyzing them individually will help us identify where we can connect EV, such that extreme conditions of peak demand and minimum voltage are not adversely affected. And this results came from this paper. All right, so what we are trying to show here, that location of EV generation is also important, where you connect your EVs. So in case one, we have a radial feeder feeding 5 houses. So we have 5 houses over here, linear loads. 5 houses have linear loads, and then we have EV either distributed or concentrated loads. So in this figure, we are showing that they are distributed between each of these houses, but we can actually concentrate it at the end, in the start, or in the middle, or we can distribute it all over the system. So if we see figure on this plot on the right, so this original load is 56 kilowatt. This original load is 56 kilowatt. We are adding 25% EV penetration. So as we add 25% EV penetration, check the voltage profile. So if we have EV load at the supply end, this plot, it will not have much impact. The second line, it will have no impact, almost same voltage profile, because the EV load is only on the supply end. And then if we have EV load at the middle, then we have little bit lower voltage profile. So voltage, we got decline in the voltage. And finally, if we add EV load at the far end, away from the generator, then how much voltage we will get? 114 or 113 volts. And these voltage dips are going more as we go away from the bus. So zero bus is the generator bus, and then as we go away from the bus, as we go bus number 10, it has the lowest voltage profile. And this plot has been plotted to show if we have generators on the both side. If we have transformer on the both side of the system, then the voltage dip will be much less. And we can see that over here we have 118, the lowest we got 118 volt, which is not bad, but it will be on the middle bus number 5. So conclusion, cumulated EV load applied at the middle of lines results in maximum voltage drop if we have transformer on the both side. All right, so how can we analyze impact of EV loading on LV distribution system? So what are the inputs and what will be the outputs of this impact analysis? So input will be existing power demand. What is the percentage of residential, commercial, and industrial customer? This information should be known. Daily load profile of these customers, system parameters such as line and load impedances of the system, they should be known. Layout of the low voltage distribution system, they should be known. So all these information should be known, and then we can do impact analysis, and the output will be this one. Existing voltage profile of the system, we will know how many EV is chargeable without adversely affecting the peak demand and minimum voltages. This we can find out. We can find out locations and identifying grid congestion, which buses will be congested. We can also know that. Installation of which charger type, slow, fast, rapid, results in minimal impact, that we will know. Of course, it will be level 1, which will result in minimum impact. So how renewable energy based solutions can minimize the impact of EV if we have DGs, and then what will be the cost of new installation? So are retrofitting the required to accommodate the desired penetration level? So all these will be outputs. And so what we are doing impact analysis of adding those EVs to see what will be its impact. Okay, so this case study is done on 33 bus system. So this study tries to analyze and quantify the impact of time-varying DGs on utility grids, considering a time-varying load both from the voltage board and harmonic. So this is 33 bus system, but what we did, we divide this 33 bus system into different load types. So if you see, this one is industrial load, and this is commercial load, industrial load again, residential load, commercial loads. And so load distribution is 50% industrial, commercial is 15%, and residential is 35%. So these numbers came from real Qatar data. We asked the data, and they told us, okay, this much is residential, commercial, and industrial load. So but however, we implemented that data on 33 bus system. So we generated our own 33 bus system based on this data. So this bus uses actual data of daily load profile to benchmark the day-long harmonic profile of a 33 bus system. It helps in identify pre-DG before connecting DG maximum and minimum point. So there are two types of DGs. One is type 1 with constant power all the time. With constant power mean they have energy storage connected with it. So they can have energy storage to feed the constant power all the time. And type 2 is varying power DG. So they have solar. During daytime they will have high power output, and during night it will have no power output. So are considered to verify deterioration of harmonic profile of entire system. So in the next step, we will check suitability of type 2, which is varying power, type 2 DG, to determine the operation in the utility grid. So how much they support voltage, let's see in the next slide. So this is 33 bus system. These are parameters per unit load, line capacity, all these parameters were used. And this is the load distribution at 33 bus system divided into industrial, residential, and commercial loads. And more data about this paper is already published here. Okay, so that's the representation of load: 38%, 39%, 23%. And so residential load is connected on bus number 2 to 14, 26 to 29. Commercial load was connected from 15 to 18 buses, and 19 to 20, and 30 to 33. And these are the load connected at industrial load. So 33 bus system is divided into different load types. Cumulatively, the power given by feeder transformer will be sum of all the load plus losses, line losses. So percentage of representation of load correspond to respective percentages of these loads which were given by Qatar utility grid. So to further analysis, important consideration is to define system power rating. And so power rating data was used from Kahrama Qatar utility grid. Kahrama is the utility operator of Qatar. So that was used to convert into per unit and do all these simulations. So on figure on the left, we have residential load profile, commercial load profile, industrial load profile, and this is all loads are in per unit. And we use 2.2 MVA base power to convert into per unit based on the data given by Kahrama. And so this is the original load profile of maximum and minimum load profile of Qatar grid given by Kahrama. Okay, so when we convert this modified, what we call modified IEEE bus system, because we are selecting some buses as industrial, uh, commercial and residential, and then we are assigning some type of load, percentage loads, which percentages were given by Karama. So that's why it's a modified IEEE 33 bus system, and this system already exists in our paper. So this is the paper, you can further read it. Okay, so what harmonic profile we use? So there are different type of percentage harmonics contributors. So one of them is PWM, adjustable speed drives. That's how much they contribute harmonics. And then we have 6 pulse converter, that what it contributes. And then we have 6 pulse. We have variable field drive. So that's that much contribution. So what we are using? We are using this 6 pulse converter. So that's which we are using, and we are using 15% of load. So total maximum contribution was 30%. So we are assuming 15% THD, and we are adding to these bus. So we are using number 8, number 14, number 25, number 30. So these are the buses with harmonic contribution. And then we have solar based DGs, which are variable. So we are using type 2. So solar based DGs are connected at 33, 32 bus, 17 bus. So 2 buses are DGs are connected. So and now we will see how the DGs and interconnection of these non-linear harmonic loads. So these power converters, a non-linear harmonic load, contribute to the harmonic and voltage profile of the 33 bus system. All right, so how we did that? So first we did fundamental frequency modeling of power system. So and to do that, we power flow analysis technique is employed to obtain the fundamental frequency bus voltages, and that's a formula to calculate bus voltages. So decoupled harmonic power analysis is used to individually obtain the harmonic components. So we using current vector and impedance vector, we calculated voltages of fundamental frequency voltages for all the buses. And then we calculated admittance matrix. Admittance matrix was used from impedance matrix, which consists of diagonal and non-diagonal values. And we combine that, and then we calculate our admittance matrix. So right now, without considering the DGs, there is currently only one feeding source, our main transformer. Feeding transformer at node 1 are suitable. So because it has some series impedance, so to convert impedance into a admittance, we selected a feasible admittance 10 raised to power minus 10 raised to power 2. So to get this admittance, we selected a reasonable series resistance impedance of the transformer. All right, so then we did harmonic frequency modeling of power system. So to do that, we have our traditional fundamental frequency component, and then we have harmonic part is a current source drawing harmonic current from the utility grid. And to do that, we have this harmonic component here in the admittance matrix. So initially it was not there, but now we have harmonics component over here, which is including which harmonic we are having in our current induction. So these are steps we use. So initially we have our resistance equivalent resistance with which we calculated with the fundamental frequency voltage. After that, from this equivalent resistance, we calculated equivalent node for node current for each of these nodes using this formula, and then we calculated a harmonic current by dividing our node fundamental current with the harmonic number, order of the harmonic. And then we calculate our THD, percentage THD, using this formula. So for estimation of THD, each of these frequency components were used to calculate THD. And for our calculating our harmonic current, these are the three steps. The first step number 1, step number 2, step number 3 to calculate our harmonic current. And so so modeling of distributed generator. So there are two, so because distributed generators, when they are made for power generation between 0.3% to 1%, this one time, so 1 per unit. If we have this much power output from generator during this time, then harmonic contribution is only 5%. But if we power output from these generators are less, between 10% to 30%, then THD contribution is 10%. If we have less than 10% power distribution, which is most of the time, so we have 20% THD contribution. So DG embedded with battery storage, if we have a battery storage and DG together, which always operates at its rated power, injects only 5% of THD. However, DG without battery storage will inject variable harmonics, and those harmonics depend on this formula, 20%, 10%. So for fundamental frequency, DG is modeled as a current source. But for harmonic frequency, nonlinear loads equation are used, and then it will be a contributor of harmonics. So in the next figure, we can see, so figure on the left, we have our fundamental frequency modeling of our system. We have 4-bus system. And so this is our grid current, and this is our DG current. DG is on the other side. So both are contributing fundamental frequency current. However, of our harmonic modeling, if we see, because fundamental frequency grid current does not contribute any harmonic, so this will be open over here. However, DG, which solar-based DG, will contribute some harmonic, so that's why it's a harmonic current contributor, contributing to system. So it depends on which harmonic order it's contributing. So it stands for order of the harmonic. All right, so let's see the impact of DG on the voltage profile. So figure on this bus number 18. So if our DG is connected at bus number 18, how it will impact. So this red one is benchmark data without any DG. And then the light blue one is constant DG. This DG is constant, then impact, this is green. So constant DG will have impact, will also correspond to the actual profile of our DG. So if voltages, it will improve all the voltages if we have constant power injection. So it has improved all. However, our time varying DGs will have no impact when they're contributing no power. So the voltage will remain same, no impact. When they start contributing power, voltage will improve also. So the same case is with bus number 25, bus number 33. And so because bus number 17 was at the end, it was the last bus in the figure 33 bus system. So voltage is going down, decreasing, and then bus number 18 is again near the generator. So that's why the voltage goes up. So addition of both type of DGs boost node voltages. They improve voltages. Constant power injecting DG type follows the same profile as benchmarking data, whereas type 2 DG, which is variable power, only provide during sunlight hours and improve voltage during sunlight hours too. Let's talk about harmonic. So harmonic profile with these both type of DGs. So if we see this gray one is a constant power DG, and it has a contribution only 5% or 4.5% contribution of THD, while the green, the blue one is a variable power DG, and it does not have any contribution when it's not producing any power, but when it starts contributing, its spikes goes very high. So it's the THD contribution is variant here. So this is the problem for designing a filtering system. So if we have a constant power DG, then we can better design a filtering system for our system. Otherwise, if we have a variable power supply, then we cannot design what time it should what time how many filters should be included in the system. So on all these profiles are same. So variable power supply has different THD profile. So in conclusion, in the early hours when power generation is low, harmonic injected by Digi2 is extremely high, extremely time varying. It's only 3%, it's low. This deteriorates the harmonic profile of the entire grid. With power varying DGs, this is I think type 1 because type 1 is constant one. So varying power DG's harmonic profile depends on the real-time power generation, resulting in further THD content inconsistent harmonic profile, and it's inconsistent for varying power DGs. So okay, so what we did, we proposed distributed filtering algorithm, and this is our 6-zone system of our marine vessel. We are getting our new NSMV marine vessel, and we tested this algorithm on the 6th zone marine vessel. And so constant power DG will be considered to restore power quality. Active filters can be included. So placement and rating of this filter must restrict maximum THD to predefined IEEE 1547 standard. It should not violate that standard. So in our previous work, we use our marine data to test this algorithm in the marine shipboard vessel to minimize THD content of the distribution system. So distribution system consists of 6 subsystems. Each subsystem is modeled and analyzed for harmonic profiling. With harmonic load assumes at different loads. And so we are currently working to extend this algorithm to 33 bus system. All right, so T1 is subsystem 1. So in subsystem 1, if we have harmonic load at bus number 5, then bus number 7 and 8 are those which are showing high THD because they are further away. So to improve those, to get rid of, to reduce those harmonic less than 5, we propose some filtering. Filter is placed as bus number 7 and total THD is reduced to less than 1%. Similarly, in subsystem 2, harmonic load was connected at node 7 and 8, and so THD was high. So filter was placed at bus number 7, and new THD profile shows THD restricted to less than 4%. Similarly, subsystem 3, we have harmonic load at bus number 4, 5, and 6. And so THD of all nodes and subsystem is less than 5%, which is fine. We did not include any filter in this case. And the paper is given here. You can read this paper for detailed analysis. And similarly to subsystem 4, subsystem 5, and subsystem 6. So filter is placed on node 8 because harmonic load was placed at node number 8 and THD was more than 5%. In subsystem 5, harmonic load is less than 5%, so we did not include any filter. In subsystem 6, harmonic load was placed at 7 node and THD was more than 5%, so we placed filter at bus number node 2. All right, so let's conclude this presentation. So transportation electrification is a leading effort to meet net zero emission target by 2050. Biden administration has invested a lot of funding in this area, clean energy. And so, but adding EV to grid impacts its voltage and stability, voltage profile, stability, and power quality. Harmonics is a concern. So to reduce their impact, adding DGs to grid is a common go-to solution to improve EV hosting capacity along with reduction in distribution losses. It also improves losses. However, increasing penetration of DGs and nonlinear loads deteriorates the harmonic profile of the system. So then we have constant power DGs with embedded battery storage, and varying power DGs without battery banks pose different challenges. So Challenge is because we have to plan, we have to decide different filter. So from simulation results presented, it is observed that source harmonics injected by time constant DGs increase THD only 1%. However, resulting profile is consistent and can be addressed by active filters. With varying time DGs, harmonic profile is depending upon real-time power generation, resulting in further high THD content, inconsistent harmonic profile. So in practice with partial shading consideration, this harmonic profile will be highly random and difficult to address even using an active filter. So that's why we should use distributed filter. So implementing a distributed filtering algorithm in this distribution system will help in governing the overall harmonic profile of distribution system, considering the harmonic content of DGs and EVs. And that's it from my side. I will be happy to take if there is any question. Thank you so much for listening to me.
Uh, Thank you, Dr. Arfan, for this informative actually lecture. It's like it has too many informations, and it opens the doors for several like research points and how to add improvements to this or that, since we are moving toward like more penetration of electric vehicles uh, for like sustainability and all these uh, goals for the future.
Yeah,
So yeah. Okay, continue.
this is a, an exciting project we are working on. People are just keep buying EVs and without considering the impact. So not only this, our power grid is not improving. We are not investing in the power grid. So if we keep adding all those EVs without considering the infrastructure improvement, it's not going to help. Houston is a big city. If if people start purchasing EVs and start connecting with our homes or the grid, what will be impact?
Yeah,
So yeah, it's an exciting
yeah,
topic.
yeah. Actually, the here for the states, actually the government like give some incentives for the people to buy more electric vehicles without like making sure that the infrastructure will be able to like to satisfy all these like scattered demand at the same time.
Right, right. You even this Biden administration adding all those funds, but there I hardly see any fund on infrastructure development. All funds are purchasing new EVs and all going to EV companies to improve and fast charging, better chargers, and thermal management of the chargers and all those things. Time range of the EVs should be increased, but there's no funding for infrastructure.
Yeah, sure, sure. Okay, so if any one of the attendees have any question or has any question, please like you have the mic. For the Michael, yeah, the presentation will be shared. We're gonna like send you all of the attendees will send the link. We share the link with you. Also, we will send the link for Dr. Arfan so he can distribute it among his like colleagues. And also thanks for Chris. He was like actually want to attend till the last point or the last minute of the session, although he has too many things to do. Okay, so actually I have a couple of questions. First one, regarding the presentation, if we can go back to the presentation, please, to the slide which has the inputs and the outputs and how we can like get these outputs according to the requirement that we should fit to that model or to the study, so we can give the output, the optimal output or optimal enhancement to the grid. Can we go back to this slide? I guess it's like 15 or
Yeah,
something like that.
let me. I have opened that. Sorry, my system is a little slow, so it takes a few
No,
seconds
it's
to
okay. It's
show the
okay.
presentation. But yeah, these all parameters, the input parameters usually are given by the utility grid and they are usually available online. Qatar grid was little bit, not uh, happy to give us a lot of data, so they only gave us maximum demand. They did not give us single line diagram of their grid. They did not give us individual penetration on each bus. So, but this, if we have this data, we have several papers on impact analysis. First thing will be modeling of the system without EV, without DG, and then we will model EVs, and then we will model DGs. We will uh, assume them placing on the existing benchmarking data, and then based on that we will see the impact. Okay, which bus is using simulation results, which bus is getting overloaded, how much is the harmonic THD, how much voltage is deviating. So all these parameters will be known from those simulation results. So all this
Yeah,
yeah.
yeah, continue.
Yeah, I think please check our paper. So these all information has already been calculated for our Qatar grid. Although the data is not actually real because 33 bus system is not the actual 33 bus system of Qatar grid, but we were given with the maximum power demand and minimum power demand profile, and based on that profile, we divided into three different loads: industrial, domestic, and commercial. And then all these were based on assumption, but the maximum and minimum profile of the load was actual profile. That's what we use.
Yeah, yeah. So my question regarding the percentage of the distribution customers, if they are like residential or commercial, industrial, because for part of that work is was about the marine or marine network or marine force system, which is like somehow different in a kind of like the customers or the not the customer, the type of loads itself, because there are like propulsions loads or something like that, which has like a complete different behavior rather than the residential or the commercial load. So the applicability of the same, like the same framework or the same design can be like fit all these applications, or it needs like some modifications, somehow to be like fit this application, fit that one, because as you know the performance of the two grids is totally different if like a normal power system or traditional power system or the marine ones.
Yeah, so actually that's a good question. It was really challenging because not all type of load comes under these three umbrella. There are some loads which does not fall into commercial loads or even industrial or residential loads. So, but we try to make a best possible approximation that which load will come under commercial, residential, or industrial load for our grid studies. But for marine study, we did not divide that load into three subcategories. We simply divide that all the buses, all the subsystems we assume for marine system, we did not divide into these three subloads. What we did, we divide the entire system into three subzones, or we call three subsystems. But we did not further divide into that. Marine was only shown to see the impact of distributed filtering in case of harmonic, but we did not divide that into different types of load. That was used only for utility grid, Qatar grid.
Yeah, and because of that, I said that this webinar is like opening the door for too many like critical points that need improvement and need to be focused on. So, like it opens like too many research points actually to delve into. My last question is like the last couple of slides, I guess, about the total harmonic distortions in the subzones. Yeah, can you go to the slide 29 because I didn't actually catch the zones exactly. So one of these zones is like zone 4 and 6. Yeah, do you have any information about the like the type of loads in this or the more details about these subzones, these subzones
So on
in terms of
marine,
like
we
load
have
demand?
different kinds of load which are not traditionally found on a utility grid. So on marine, our main load is the propulsion load to propel
Yeah.
the entire vessel. And then we have lightning load, then we have air conditioning load, then we have electronic load. People charge their phones on the vessel. So the loads which we get is purely different, and they are more kind of constant loads. If vessel is not at port, if it's traveling in the ocean, then the load is almost constant. Propulsion is still there, HVAC, air conditioning is there, electronic load is there. Their dining has a lot of load consumption because everything is on the vessel. So yeah, these are different types of load which we have in the entire system.
Yeah. 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 Thank you so much, actually, Dr. Arfan, for your time first, and for your like information, which is like too informative session, actually, for me, for myself, at least, and I'm sure that the other colleagues also will enjoy this session. And I'd like to share your my Ibtissam Kharshuf, my colleagues, actually is sending like her greetings for you for this presentation. She's the chair of IEEE Young Professional and We Affinity Groups here at Miami section, and also the chair of IEEE FIU PES Student Branch Chapter. And we are so happy that we have you today, and we hope to join us in the coming webinars soon.
Sure. Thank you so much for invitation. I really enjoyed talking today. Have a
Thank,
great day.
thank you, Dr. And I'm gonna send you the link for this presentation.
Yes, please. Yeah, thank you. Thank you.
Cool.
Okay, take
Thank
care.
you so much. Thank you for you all attending. Thank you so much.
Thank you. Take care. Bye bye.
Bye.